Hey there, grade 12s, and welcome to our final unit on redox chemistry. Redox is an abbreviation. It stands for the words oxidation and reduction. And just from the sound of the title, you can kind of get the idea this has something to do with oxygen. And originally, that's what people thought oxidation was. They thought it was combining with oxygen. When carbon combines with oxygen, when we burn a match, one of the products that we get is carbon dioxide. When iron rusts and combines with oxygen, we get iron oxide. Those are both oxidation reactions. Reduction then meant removing oxygen. And it's interesting that if you react rust, iron oxide, with carbon, the carbon will pull the oxygen off of the iron, pull the oxygen off the rust, and restore to elemental iron. So originally we thought oxidation was just adding oxygen and reduction was just removing it. And that is true, but there's a lot more reactions that can be considered redox reactions. The terms oxidation and reduction today have a much broader definition, but in order for us to understand what it is to be a redox reaction, we're going to have to learn how to assign oxidation numbers, and that's going to be the point of today's lesson. Oxidation number is the apparent charge on the atom. What charge it looks like the atom has in a particular compound, because it's not always what you'd expect it to be. We have a list of rules that we can go through, and you have these in your notes. And there's lots of different versions of this list, but they're all essentially the same. When we have any uncombined atom, an atom in its free state, just its elemental state, we don't see a charge on it. If I've got a sodium atom or a calcium atom, or even if I have elements that are molecular when they're elemental state, like hydrogen or oxygen, which are diatomic, we don't see any charges on any of these things, and they don't have any combination to other elements. So we define their oxidation numbers as being 0. If you see an element by itself, and there's no charge, you assign the oxidation number of 0. When we have compounds, for example, these compounds here, we have a couple of other rules we'll do. Hydrogen almost always gets an oxidation number of +1, which is what we'd expect. We know hydrogen likes to form +1 charges as an ion. There is an exception when hydrogen bonds to metals. Hydrogen's actually got a stronger electronegativity than most metals, so it tends to pull the metal's outer electron toward itself. So then hydrogen gets an oxidation number of -1, but only if it's attached to a metal. Any other alkali metal, sodium, potassium, lithium, anything down group 1, will always get a charge of +1 in a compound. Our alkaline earth metals, our group 2s, always get a charge of +2 when they're in a compound. And this is exactly what you'd expect. So that's pretty easy. When we have oxygen as part of a compound, it almost always likes to take its normally expected charge of -2 as well. Again, there's an exception. When oxygen, it's in a peroxide. Remember, per means one more than you'd expect. For example, hydrogen peroxide, it only gets a charge of -1. Fluorine and any of the other halogens tend to have charges of -1. Fluorine, being the most electronegative, will always have a -1 charge. The other elements can actually change, but usually they're going to get -1. How do we figure that out, whether it's going to be -1 or something different? Well, at the end of the day, it all comes down to this. When I have a chemical compound, I've got a group of different atoms bonded together. Their oxidation numbers will always have to add up to the overall charge on the compound. If it's a neutral compound, that means it adds up to 0. If it's an ion, it'll add up to the charge on the ion. So let's go through a few examples of this. Here are 2 different acids. We've got sulfuric acid and sulfurous acid. How do we assign the oxidation numbers for each individual atom? Now, I want you to remember, as we assign oxidation numbers, I want the oxidation number on each atom in the compound. We're going to have to think of the total number of atoms, but we always assign them on a per atom basis. Let's start with the sulfuric acid. We've got a rule for hydrogen. Hydrogen, unless it's attached to a metal, gets a charge of +1. So I know its oxidation number will be +1. And oxygen, unless it's attached in a peroxide, which this is not, gets a charge of -2. So far, we have +1 on each of the hydrogens and -2 on each of the oxygens. Again, oxidation numbers are assigned on each individual atom. But we have to consider how many atoms there are in total to figure out what the charge will be on the sulfur, the oxidation number. I know I have 4 oxygens, each with a charge of -2. 4 groups of -2 gives us a total charge so far contributing to this molecule of -8. We also have 2 different hydrogens, each with a +1 charge. So 2 groups of +1 contributes a charge of +2. Overall, we notice that this atom doesn't have a charge. If it had a charge at all, it would have been written here, and it doesn't. So we can assume that once I've added up the oxidation numbers of all the individual elements, the overall charge has to add up to 0. -8 and +2 tells us so far we're at -6 for a charge. The only possible charge that sulfur could take would be +6. So the oxidation number on sulfur in sulfuric acid is +6. Apparently, in sulfuric acid, sulfur takes on a pair charge of +6. It means that 6 of its electrons are pulled farther away from itself and towards the other atoms in the compound. Now, that doesn't mean sulfur will always have an oxidation number of +6. Let's consider sulfurous acid. Again, we know that we have rules for assigning oxidation numbers for oxygen and hydrogen. In this case, however, there's only 3 of the oxygens. So we have -6 coming from the -2 on each of 3 oxygens. We've got +2 coming on 2 hydrogens, each with a +1 charge. And again, because there's no overall charge on this particular molecule, this has to add up to an overall charge of 0. In this case, sulfur is going to take on an apparent charge of +4. The oxidation number of sulfur in sulfurous acid is +4. When we assign oxidation numbers, again, remember that I always want you to write down the number, the oxidation number, the charge on each individual. I like to, for myself, write oxidation numbers immediately above each of the atoms. Some people like to write them below. Whatever you do, make sure you don't write them in the place of the charge in the upper right-hand corner. Now, technically, +4, -2 are oxidation numbers. Charges are usually written 2-, so I've got this one kind of written a little bit backwards. Let me fix that for you. There, now that's a little better. At the end of the day, I'm never going to take off marks if you write -2 or 2-, but some scientists and some of the universities that you might go to may make a big deal about this. So just be aware of it and do what your prof prefers for you. Now, in this case, we don't have a way to assign a number for sulfur, but we do for oxygen. Also in this case, the overall charge is going to have to add up to -2. So I can see that I've got 2 oxygens times whatever their oxidation number will be. I see only 1 sulfur in this grouping times whatever its oxidation number will be. And because there's a -2 charge here, I can see that the overall sum of all of the oxidation numbers has to add up to -2. We know that -2 is the oxidation number on an oxygen. So far, we've got -4 for a total charge. In order to make this statement true, we would have to assign a charge of +2, an oxidation number of +2 on the sulfur. 1 group of +2 and 2 groups of -2 adds up to the total overall charge of -2, 2 minuses, which is the oxidation number on the SO2 2- ion. There are a few YouTube videos I'm going to get you guys to watch to get you to practice assigning oxidation numbers. I'd recommend that you work through the examples that you see and have a copy of them because they'll help you, and understanding how to assign oxidation numbers is fundamental to this unit. Now that we know what oxidation numbers are, we can actually have the more broad definition of oxidation and reduction. When we look at a chemical equation and we see that the oxidation number as the reaction proceeds appears to go up. For example, in this equation, before the reaction, we can see sodium by itself as an element has an oxidation number of 0. And after it reacts in a compound, it has an oxidation number of +1. Its oxidation number appears to have increased. So this is now our new definition of oxidation. My oxidation number appears to increase. The reason this happens is because sodium loses one of his electrons to the chlorine. So electrons are lost. Reduction then happens anytime the oxidation number appears to go down. Before the reaction, each chlorine in diatomic chlorine, because it's an element by itself, has an oxidation number of 0. However, after the reaction, in the compound sodium chloride, chlorine has an apparent charge of -1. It looks like the oxidation's gone down. To make its charge per atom appear to get more negative, it has gained an electron. Reduction is a decrease in oxidation number caused by a gain of electrons. There are a couple of ways to remember this. My favorite is the phrase Leo says Ger. Losing electrons is oxidized, so my oxidation number goes up. Gaining electrons is reduced, so my oxidation number goes down. Some people prefer the acronym OIL-RIG. Oxidation is the loss of electrons and reduction is the gain. Either way, it's important for you to remember whether a substance has been oxidized or reduced. Remember that anytime electrons are lost, my oxidation number gets bigger, that's an oxidation, and the opposite being a reduction. Two more words I want to give you to practice is the agent, the thing that causes it. Now this is always the opposite of what was oxidized or reduced. Take a look at this example. In this case, zinc before the reaction is an element by itself, so its oxidation number is 0. In copper to chloride, we assign the chlorine, the most electronegative gets assigned first, as -1, and the copper, each of them will have a +2 oxidation number. 2 -1s and +2 adds up to the overall charge of 0 on this compound. After the reaction, chlorine still has an oxidation number of -1, but zinc now has an oxidation number of +2. Copper's oxidation number has changed to 0. There are two species whose oxidation numbers have changed. Zinc's oxidation number has gone from 0 up to +2. Because its oxidation number went up, it was oxidized. So we're just going to put ox for oxidized. Copper went from +2 before the reaction down to a charge of 0 after. Copper was reduced, so I'm just going to put R for reduced. Chlorine did not have its oxidation number change at all. Chlorine is what we would call a spectator. In a chemical equation, an atom whose oxidation number does not change is called a spectator. So if zinc was oxidized, it lost electrons. If copper was reduced, it's because it gained electrons. Now they didn't just lose or gain them from anywhere. When zinc lost his electrons, he forced them onto the copper and caused the copper to be reduced. Zinc then, because it caused the reduction of another species, is my reducing agent. So the species that was oxidized becomes the reducing agent. Now we can look at this from the opposite point of view. Copper was reduced because it gained electrons, but where did it gain them from? Well, it ripped them off the zinc and forced the zinc to be oxidized. So because copper caused another species to be oxidized, we call it the oxidizing agent. And I'm apologizing for my bad writing here using a mouse, but this is what we got. That's supposed to be an O, not a D. We have the reducing agent, is the species that was oxidized, and the oxidizing agent being the species that was reduced. So I want you to pay attention to that as you go through the practice. We have lots of practice available for you. There's a lot of practice in your textbook in Chapter 19. There's questions 1 to 14. Also, the very first worksheet in the workbook section of your reduction oxidation book. You'll notice that there's a big chart there about standard electrode potentials. We're going to save that for later. But on the second page of the workbook, you'll see 15 review questions. 1 to 10 are on the first page, and 11 through 15 on the second page. You'll also notice that there are answers included beside you all the way through to help you see if you've marked it right. In a few places, the photocopying didn't work out great, and it's changed some of my pluses to minuses. So if you see something that looks a little weird there, just message me and I'll send you a correction. But this is a really important foundation for the unit. So before you get into all of this, definitely watch those YouTube videos that I'll post below this and work through the practice problems.